Thank you, Johan, and thank you, Gabriel, for the invitation to give this talk. So I'm happy to give this talk as a PhD student of the new generation who was working on deep learning. And so the goal of this talk is to give you some insights that I got on neural networks with a few layers as a practitioner, because I'm someone who cares a lot about applications. And maybe before going into the details, I'm going to put a bit of context about the works I would like to mention today. And so I was one of Stefan's PhD student from 2013 to 2017. And so I was working on image classification. And of course, as most of the PhD students of Stefan now, I was working with the scattering transform. And so our goal was to focus on understanding if group variabilities, which means here geometry, geometrical arguments, and this kind of elements, were a good model for image classification. And at the same time, where I was beginning my PhD, so the field of deep learning was really exploding. And it has made this PhD very interesting for me because, I had at the same time a PhD advisor who wanted to do a lot of mathematics. And on the other hand, I had the opportunity also to learn new ideas from the deep neural network, the deep learning field. And so, if I may, there are also a couple of elements which made this PhD, to me, really cool and original. So I worked on many baselines that researchers, in particular in deep learning, they sometimes found a bit strange because, for example, we are trying to solve deep learning tasks by involving a limited amount of learning and this kind of elements. But what I really did appreciate is that all those baselines, they were really motivated by mathematical arguments. At the same time, incorporating mathematical structures in deep neural networks, that's a task that was quite difficult, even if I hope we put some structures in them. And one of the reasons, and I guess some of the PhD students of Stefan now might have the same feeling, is that sometimes principal models, it can be very slow to run. I can also testify that those facts happen in Stefan's team. So, I think the moment, like the year where T3 happened was in 2016, if I'm correct. It's when we went from MATLAB to PyTorch, for example, going from CPU, where we're using limited learning. So what I mean by limited learning, for example, training SVM on those cluster at the NS, going to some hybrid or end-to-end learning and using GPUs. Going from conferences of single processing to iClair, that was a big gap, or even going from MNIST to suddenly ImageNet, and trying to go from group invariance to, I would phrase it as an open question. So it was quite interesting because I feel it's a very different perspective from what other people were doing in computer vision groups or in other kind of machine learning groups. And let's get back now to image classification. So there is, and I think this slide, even if it's super basic, is quite important to really understand the motivation of using shallow learning or limited learning. If you think about it, when you want to classify images, and that's something that Stefan kept telling me for many years, you really need to solve a very difficult problem because you have a lot of samples, and despite the fact you have a lot of samples, the dimensionality of the samples is super high, which means that at the end of the day, you have few samples compared to the ambient dimensions. So in fact, performing an image classification task on a dataset like ImageNet, it's something which is quite involved and quite difficult. So if you think about it, when you're solving a deep learning task, you're doing something which is quite extraordinary, in particular for image classification. However, we tried to put some principles on those ideas from image classification. So in particular, by developing some framework where we have some models of geometric variability. So for example, translation, rotation of an image, scaling. There are also some other group of variabilities which go beyond geometrical groups, like for example luminosity, occlusion, small deformation, and this type of variabilities which have an explicit formula. And on the other hand, we had class variabilities, for which there were no a clear model of how we could use them for image classification. And there were two ideas that Stefan proposed and that we tried to incorporate as structures in our neural networks. So the first concept, it was this idea to memorize level sets. So where you want, for example, to either span the full level set of a given class, or either you want to learn to separate the different level sets. Unfortunately, this kind of strategy is doomed to fail, because it's very likely that those level sets are in high dimension, and so you need really an exponential number of samples, which is something which is getting impractical given the number of samples, for example, in ImageNet, where you got only 1 million samples. So there is a single idea, which is this notion of invariance, where there is this assumption that there exist some level sets and some symmetries which are going to preserve those level sets. So for example, one of the great examples that you can think about is translation, and the fact to have a cat on the left corner or the top right corner gonna bring you an invariant, and if you want to get an invariant, you simply need to do an averaging along the orbit of this symmetry. Unfortunately, there is again another issue here, which is that if you want to estimate the symmetries, they are potentially in high dimension, and thus you might have we might struggle to estimate them. And so, at this point, what I would like to challenge is just to wonder if image classification might be solely simpler. So it's a bit a provocative claim, in particular given the number of engineering tricks which are needed to train deep neural networks. And I just want to challenge those ideas and wonder if we could use a simpler architecture to try to solve ImageNet benchmark. So I'm gonna do something slightly interactive, in the sense that with Stefan, we had this bet. So, I mean, it's not me who actually took the bet, because if it was me, probably that would have been more, I would have been more careful. So during my PhD studies, so Stefan was talking with another researcher, and so the kind of bet together that before the end of my PhD, we could reach the AlexNet accuracy. So this FAME model that came up in 2012. Purely and solely with a geometrical representation, which means basically the scattering transform, if I understood correctly.
No, anything.
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 Fair. Perfect.
Anybody. Not just we, anybody.
Well, let's say that it was kind of a challenge you might have put on my shoulder. And so, I mean, I guess we might have lost, or because...
And you should say, it was a serious bet. It was a 3-star Michelin restaurant. So it's not just a small bet.
If I may ask, did it happen?
Of Of course.
Oh.
I did invite Jan for 3-star. Yeah.
So, despite the fact we lost, it's still unclear to me if it's feasible to reach an AlexNet accuracy by involving purely and solely geometrical arguments. So, what I mean here is to avoid any refinement that you could use with backpropagation or end-to-end training. So that makes really tricky learning, because as you might know, deep neural networks, they have this tendency to specify the bias of their architecture thanks to backpropagation. So it's a quite difficult task. However, I mean, after a couple of years and looking more carefully to some works that I did or could have been done indirectly, in fact, I have the impression that we try to solve this question, which is what is the best accuracy that you could get from a shallow architecture. So what I mean here is simply a 2-layer neural network on modern hardware, right? That's one of the constraints. So why shallow CNN? So just to be clear, when I mean 2-layer neural network, I mean two hidden states, pardon. So two non-linearities, basically. So there are a couple of reasons to consider this kind of architecture. So for example, from a theoretical point of view, they are simpler to analyze because there are less layers, and you know that depth is something that makes it tricky to analyze, because maybe at the first layer you have access to the topology of the signal, which means that you can read directly the weight of the filters, and for example, having a nice structure on the first layer is something that is expected. So you want to focus on shallow neural networks. There, having 2 layers is a bit more tricky to analyze, but you can still say some things. And you know that 2-layer neural networks have better approximation properties than one hidden layer neural network. Also, from an engineering point of view, they are simpler to evaluate. You can achieve more parallelization and this kind of useful elements for applications. For example, to do boosting or this kind of elements. And if you think about it, like I think during the 2 days, there were a lot of mentions of those quite shallow architecture, because we can understand them in a better manner. And so what I would like to discuss is actually how good are those 2 layers architecture on data sets like ImageNet. So let's try to see how far we can go solely with 2 layers. So there is a kind of betting time, and I would like you guys to try to think about it, because so try to think again about this ImageNet dataset where you have 1,000 classes, which means that basically you need a couple of sheets of paper to try to figure out which label is an image. You have labels like forest, cat, cloud. What is the appropriate label for a given task? So first simple question, what is the accuracy of a random classifier if you have 1,000 classes? Yeah. Perfect. So top 5 is going to be about like 0.3%. And what about an AlexNet? So the AlexNet accuracy on the ImageNet dataset is about 80%. Which means if you go from a random classifier which is achieving a correct classification at a rate of almost 0, let's say, you're going to go to 80% with an AlexNet. So, in your opinion, how far can we go with one layer, one convolutional layer on ImageNet? 60? Okay, we think like more than 50. Okay, you're pretty audacious. We think more than 20. Okay. That's great. Good to know. So if you apply simply a deep neural network trained in an end-to-end manner with any cooking recipes that you might know to train them, like batch normalization, trying to make them as deep as you can, as wide as you can, using any normalization technique. One layer gonna get you up to 25%. Two layer gonna get you up to 44%. So I'm talking, of course, about accuracy, right? Accuracy. So, and so baseline, which is interesting because first of all, it's fairly simple to implement. I mean, right? And fairly simple to train as well. But I was not aware of it except in one work with Eugene. So the main reason we were not able to increase the performance is because this task is pretty conditioned. Like even on the training set, you're not going to be able to overfit your neural network.
But
yeah.
Sorry to interrupt. The one hidden layer, you can convert them into convex optimization problems. Like there's a group plus soup formulation of these things. So you can solve this to global optimum, no problem.
You're absolutely right. However, there are a couple of tricks that you want to incorporate. For example, like data augmentation, which suddenly makes very impractical these kind of things because you need to use SGD, data augmentation, which means having a couple of epochs. And for example, you cannot use strategies like storing the features on some computers and then training a linearized VM or a linear classifier. But that would be great if we could employ such strategies.
Once I have a convex formulation, I can have a decent algorithm that will have decent. I don't need to solve it to like 10 digits of accuracy. I'm just going to go down. I'm not going to enter a local minimum that is not good. I mean, it's a good world, right?
So second issue, the problem is pretty conditioned, which means that if you want to achieve a good accuracy, you will need to train it for a long time. And I think the eigenvalues when you look at your covariance matrix, you're going to see something which is really poorly conditioned. So, and then you can tell me, yeah, you can incorporate some regularization, and trust me, we kind of tried those things with one of the PhD students of Stefan, Luis, but we are not able to get good accuracies, unfortunately. So, there is the second method. And when I put the years there, they correspond to the first year of where the representation was developed. Because in 2007 there was no computation resources to work with the scattering transform on ImageNet. So, in your opinion, is the scattering transform doing better or worse than a two-layer neural network? That's pretty correct. So scattering transform with Gabor wavelets. Gonna bring you to 45%. So let's say it's about the same. So that's one of the story of the scattering, where the scattering is doing about the same as deep neural networks. Just maybe one word about the way we were able to scale the scattering thanks to a framework, ImageNet, which has been sponsored notably by the NS and the Flatiron Institute. So I think all the PhD students of Stefan, other collaborators are really thankful because having a GPU acceleration is now pretty useful, in particular for the scattering. All right. So at this stage, we have two baselines, one which is well motivated from a mathematical point of view, the scattering transform, and another baseline which is deeper learning related. I'm going to go in something which is even more provocative. What about going simply into patches? So I'm going to describe you the pipeline there, which is fairly simple. You get an input image, you decompose your image as its overlapping patches, right? So it's pretty redundant. Assume that you have stored somewhere some dictionary, obtained from some random patches, and then for a given patch, assign its Q nearest neighbor. So it's a very way to obtain a representation because you want some invariance to translation you perform some local averaging given some spatial windows, which means that at the end of the day, because we use here some hard quantization, you obtain a representation which is made of integer numbers, right? So, same question, in your opinion, is it doing about the same as a scattering transform as a deep neural network or better? That's a super simple baseline, which, I mean, should be simple to analyze. I always struggle to do so, but maybe someone will succeed in doing this. And, you know, when you look at the patches that we use, one of the constraints we had was to avoid using any backpropagation on the dictionary. So basically, we just apply whitening so that you see that the patches we use in the dictionaries don't look like wavelets, they just look like corners that span multiple directions, that have multiple colors. And at the end of the day, this is getting, to me, a quite impressive accuracy. So using a linear classifier, we are getting something about 60% top 5 on ImageNet, which is, you know, there is a significant gap with deep neural network there. If you apply one more convolutional layer, suddenly you're able to get a few extra %. But, you know, solely this representation with a linear classifier, to me, it's super impressive. And so here it's completely convex. So we can train again very easily a linear classifier, and that's what we did. But unfortunately, as I mentioned, it's the same thing as for the one hidden layer neural network. This is not a pretty ill condition. So we could not use any trick to, for example, to have something which is fast enough so that we can train larger models, because now I'm going to go in the hyperparameters of our method. So there are 4 hyperparameters: the size of the dictionary, the patch size, the number of nearest neighbors, and some regularization parameter for the covariance matrix. So this is obtained on CIFAR10, and I know we're not used anymore to this kind of things where we show a validation set to pick the best hyperparameter, but here it's very important because there is no learning involved except the linear classifier. And for example, on CIFAR10, we're able to get competitive results with deep neural networks by using something like 60,000 patches. On ImageNet, we had, for computational reasons, to downsample the signal from an image of size 224 to 64. We had to limit ourselves to 2,000 patches to use quite a huge number of nearest neighbors. This is always a surprise to me because I would have expected those patches to be, you know, unbetting in some low-dimensional space. But the number of nearest neighbors that we use is something which is important. That's a surprise. Super small patches, 6 pixels only for the dictionary. And so the number of the weight decay was fixed. So the method, which is actually getting the state of the art for this, let's call it benchmark, it's Fisher vectors. So Fisher vectors, that's some representation which were designed by Jacob Verkib and Florent Perronin. And so the idea is again to split an image as its overlapping patches. So that's the same initial pre-processing step. And then you feed those patch descriptors to say, so here some Fisher vectors or some sparse dictionary encoders. And from that, you feed the final representation after an average pooling to a linear classifier. And that gets you the state of the art, which is about 75, if I'm correct. So looking at those numbers, to me, it's one of the first time I see a baseline where the deep neural network is the last. And, you know, principal methods that were used prior deep learning are doing slightly better. So I think there is a kind of shallow challenge here. In the sense that there is a super wide literature where people are doing teaching students, do deep neural networks needs to be deep, and this kind of, you know, other, let's say, challenge where people try to constrain a lot of their neural networks. One of the questions, I mean, I think it's pretty interesting also given like how promising would be the patch-based method, how good can we do with a two-layer neural network with a model architecture. So in conclusion, personally, I think that choosing different baselines, different challenge, simplified task goals from what we normally use in deep learning could help to get out of this local minimum of understanding deep learning, because suddenly you really have to be smart about the way you're going to combine your features and train your models. Also, I mean, that's one of the examples where deep learning a priori is not doing the best accuracy in a given baseline. So, of course, until I'm proven wrong, and I know how people can do in deep learning. And I'm not. Happy birthday, Stefan.
All right, questions for Edouard. John.
Yeah, so if you go to the batch slide,
yes.
There's a curve that seems to, so blue is accuracy, not the other.
Oh, sorry, this one.
Yes. So it seems that if you could have resources to increase the dictionary size, you know, the curve seems to be going in the right direction.
You're absolutely correct. So to a kind of disclaimer, so this is on CFR10, first of all. We verified that indeed on CFR10 we can get a supervised accuracy, but like I don't think Luis was able to get. Luis is not here. Oh, too bad. That Luis was able to get something with more than 2,000 patches. If you think about it, we solely used 2,000 patches on ImageNet, and we're able to get a super good performance, which is non-trivial at least, much better than a random guess and many other baselines. So
you don't think that with more patches you would get better?
Of course, but like I don't have the cluster.
Okay, so it's really computation.
I don't know. I mean, to be honest, I think there is a limit. I don't know where is the limit, but I think it's a great open question, because what's the message behind that? If this method was working, it would mean that image classification could be simply a gigantic nearest neighbor classifier, in some sense. And that would be really cool. But like, of course, this needs to be numerically demonstrated. I don't have the...
Any other questions for Edouard? Not that I see. All right, let's thank Edouard again.